Neural networks are like the brains of computers. They can learn to do amazing things just like our own brains. One of their coolest tricks is recognizing handwritten digits. Imagine you write a number on a piece of paper. A neural network can look at your writing and tell you what number it is. This might seem simple, but it's actually a very hard problem for computers to solve. Neural networks are good at this because they're inspired by how our own brains work. They have millions of tiny parts called neurons that work together to process information. These neurons are connected to each other, forming a complex network that can learn from data. A neural network is made up of layers of neurons. The first layer is called the input layer. This layer receives information from the outside world. For example, if we're trying to recognize handwritten digits, the input layer would be a grid of pixels representing the image of the digit. The last layer is called the output layer. This layer gives us the result of the network's computation. For our digit recognition example, the output layer would have 10 neurons, one for each possible digit from 0 to 9. The neuron with the highest activation would be the network's prediction for the input digit. In between the input and output layers, there are one or more hidden layers. These layers are where the magic happens. The neurons in the hidden layers process the information from the input layer and learn to extract features that are relevant for the task at hand. Each connection between neurons has a weight associated with it. The weight determines how much influence one neuron has on another. Think of it like a volume knob. A higher weight means a stronger connection and a lower weight means a weaker connection. In addition to weights, each neuron also has a bias. The bias is a constant value that is added to the weighted sum of inputs to a neuron. This helps to control the overall activity of the neuron. The weighted sum of inputs and the bias are then passed through an activation function. The activation function introduces non-linearity into the network. This is important because it allows the network to learn complex patterns that cannot be represented by linear functions. But how does the network learn the correct weights and biases for a specific task? This is where training comes in. During training, we show the network a large data set of labeled examples. For example, in handwritten digit recognition, we would show the network thousands of images of handwritten digits, along with their correct labels. The network then uses an algorithm called backpropagation to adjust the weights and biases so that it can correctly classify the training examples. This process is repeated many times with different sets of training examples until the network achieves a desired level of accuracy. And that's it. In a nutshell, that's how neural networks work. They are powerful tools that can be used for a wide range of tasks, from recognizing handwritten digits to translating languages and even driving cars. As we continue to develop and refine these networks, who knows what amazing things they will be able to do in the future.